deep into what is arguably the most fundamental concept in all of survey statistics, simple random sampling. Seriously, this is the bedrock. Once you master this, pretty much every other complex sampling method will make a whole lot more sense.
All right, so here's our game plan for this explainer. We're going to start with the absolute basics. What is simple random sampling, really? Then we'll get into the good stuff, how we use a tiny piece of a population to make big, bold claims about the whole thing. We'll even pop the hood and look at the mathematical proofs that make all of this trustworthy. After that, we'll tackle a super common scenario with proportions, wade into the tricky waters of confidence and uncertainty, and finally, see what happens when our samples get nice and big.
Okay, so first things first, let's get really precise. What do we actually mean when we say simple random sampling? It's a term that gets thrown around a lot, but in statistics, it has a very, very specific definition.
And here it is. This is the heart of it. If you have a big population of n items and you want to pick a smaller sample of size n, a simple random sample means that every conceivable group of n you could possibly form has the exact same chance of being the one you pick. Think of it like the ultimate fairest lottery draw.
Now, a really important consequence of this is that the probability of any single person or item ending up in your sample is just your sample size, n, divided by your population size, n. It's that simple. This little ratio is really the cornerstone of what makes this whole method fair.
But hold on. This leads us to a super important question, and honestly, a pretty common point of confusion. Let's say you set up a system where every single individual has, for example, a 1 in 10 chance of being picked. Is that enough? Does that automatically make it a simple random sample?
The answer is a huge no, and this example shows you exactly why. Imagine you have 100 people sitting at 20 different tables, with 5 people at each table. Now, you decide to randomly pick 4 of those tables and survey everyone sitting at them. Well, every person has a 4 in 20, or a 1 in 5 chance of being in your survey. That seems fair, right? But here's the catch. Is it possible for your sample to have one person from each of the 20 tables? Nope. Absolutely impossible with this method. And because not all possible combinations of 20 people can be formed, this is not simple random sampling.
So, we've gone through the trouble of getting a true simple random sample. Awesome! Now what? Well, this is where the real work begins. How do we take the data from this small group and use it to say something smart and meaningful about the entire population?
Typically, we're trying to figure out 2 main things: the population average, or mean, and the population total. And the way we estimate them is pretty intuitive. Our best guess for the population mean is, well, the mean of our sample. Makes sense. And to get our best guess for the population total, which we call t-hat, we just take our sample mean and scale it up by the size of the whole population.
And this right here is where the magic of simple random sampling really shines. Our sample mean has 2 incredible properties. First, it's unbiased. That's a fancy way of saying it doesn't systematically guess too high or too low. Over the long run, on average, it's gonna be spot on. Second, we have this exact formula for its variance, which tells us precisely how much our sample mean is expected to bounce around the true value. Let's zoom in on that variance formula for a second, because that first part is really important. It's called the finite population correction, or FPC. This is our adjustment because we're not putting people back in the pool after we sample them. And as our sample size n gets bigger and closer to the population size n, this whole term gets smaller, which shrinks our variance. It makes perfect sense, right? The more people you sample, the more certain you become. And if you sample everyone where n equals n, your variance drops to 0, because you know the answer exactly.
So I've just told you that our sample mean is unbiased and that we know its variance, but in statistics, we don't just take things on faith. So let's actually go under the hood for a minute and look at the elegant math that guarantees these properties are true.
Now, the secret weapon for these proofs is a ridiculously simple but brilliant little tool called an indicator variable. We'll call it z sub I. All it does is act like a light switch. It's 1 if the ith person is in our sample, and it's 0 if they're not. And we already know the probability that this switch is flipped to 1. It's just n over n.
Let's just walk through this proof. It's actually way more straightforward than it looks. First, we just rewrite the sample mean using our new z variables. Then, we take the expectation of the whole thing. And because of a wonderful property called linearity, we can just slide that e right inside the sum. Now for the key step. We know the expected value of zi is just n over n, so we substitute that in. You can see the n's cancel each other out, and what we're left with is the exact definition of the population mean. Boom, proof complete.
All right, the variance proof is a little more involved, but it all hinges on understanding one more concept:
Covariance. See, since we're sampling without putting people back, once we pick person I, they can't be picked again. This means that picking person I ever so slightly lowers the probability of picking person J. This relationship, this slight negative dependency, is what we capture with covariance.
So, without getting lost in all the algebra on screen, here's the big picture for the variance proof. We expand the variance of the sample mean, and it blossoms into this big expression full of the variances of all our indicator variables and, crucially, all the covariances between them. It looks like a mess at first, but after some clever algebraic simplification, tons of terms cancel out, and we are left with that exact beautiful variance formula we saw earlier.
Okay, let's shift gears now and talk about something you will find yourself doing all the time in the real world: estimating a proportion. Like what percentage of people approve of a new policy. It feels a little different than estimating a mean, but as we're about to see, it's actually the exact same problem, just wearing a clever disguise.
And this is the beautiful connection. To handle a proportion, we just turn our data into simple ones and zeros. A person gets a 1 if they have the trait we're interested in, and a 0 if they don't. The mean of all those ones and zeros in the population is the population proportion, p. And the mean of the ones and zeros in our sample is the sample proportion, p hat. So a proportion is just a mean, which is awesome because it means all that theory we just worked so hard to prove applies here automatically. And you can see here how nicely our general formulas simplify when we're dealing with proportions. The population variance, s squared, just becomes this neat little expression involving p times 1 minus p. And that, in turn, makes our formula for the estimated variance of our sample proportion much, much cleaner to calculate.
Okay, so we have our estimate. Say our sample shows that 45% of people are in favor of something. But that's just one number from one sample. We know that if we took a different sample, we'd get a slightly different number. So how much faith should we really put in that 45%? This is where we need to start talking about confidence intervals.
To really get what a confidence interval is all about, let's imagine a tiny little toy world. We have a population of just 8 units, and we happen to know the true total is 40. Now let's say we draw samples of size 4. Because this world is so small, we can literally list out every single possible sample we could draw. For each one, we can calculate our estimated total and build a confidence interval around it. And what you see is that some of these intervals manage to capture the true value of 40, and some of them just miss.
So if we actually go through all 70 possible samples for this little population, and we use this specific method for building our intervals, we find something really interesting. 54 out of the 70 intervals, or 77% of them, successfully contain the true population total. That's 77%. That is the actual confidence level for this specific procedure in this specific world.
And this brings us to probably the most crucial and most misunderstood point about confidence intervals. In the real world, we only get one sample. We calculate one interval. And we never ever know if we got one of the good ones that hit the target or one of the bad ones that missed. So when we say we have a 95% confidence interval, it doesn't mean there's a 95% chance our specific interval is right. It means we have confidence in the method, that if we were to do this over and over, the method would work 95% of the time.
Obviously, in the real world, with thousands or millions of people, we can't list out every possible sample. So how do we build confidence intervals then? Well, the answer comes from one of the most powerful and beautiful theorems in all of statistics.
Meet the central limit theorem. This is basically our statistical superhero. It tells us that, as long as our sample is big enough and our population is big enough, the distribution of all possible sample means will look like a beautiful, predictable bell curve, the normal distribution. This is an incredibly powerful result.
And because of that theorem, we get this practical workhorse formula that statisticians use every single day. To get our confidence interval, we take our sample mean, y bar, and then we add and subtract some multiple of the standard error. That multiplier, that z-value, comes directly from the standard normal distribution, which the central limit theorem gives us permission to use.